Welcome back to The Explainer. Today, we are diving headfirst into the absolutely beautiful, almost magical geometry of calculus. If you've ever sat there and wondered how the math we do jumps off a flat page and actually materializes into the three-dimensional physical objects we use every single day, well, you are in the perfect place. Let's get right into it.
Let's start with a really practical, real-world hook. Think about a perfectly curved dog bowl, or, a funnel, or even a glass light bulb. How do manufacturers figure out the exact amount of material they need to make those? Everyday objects like these completely defy simple elementary geometry formulas. You can't just do a quick length times width times height calculation here. We need a much more powerful tool to actually map out those continuous curves.
To get there, we really have to ground ourselves in a core mathematical truth from our sources. From a geometric standpoint, the definite integral is area. An integral isn't just some abstract algebra problem meant to give you a headache. It is fundamentally tied to physical space. It's basically the numerical footprint of a shape. And today, we're going to take that flat 2D footprint, grab it, and pull it right into the 3D world.
So here's our roadmap for the explainer today. First, moving from 2D area to 3D space. Then we'll break down the big three, the disk method, the washer method, and cylindrical shells. After that, we'll cover the golden rule of rotation, and finally, we'll see all of this pay off in some real-world calculus.
All right, section 1, from 2D area to 3D. Let's start pulling that flat area out into physical space.
You've definitely seen this setup before. It's where calculus usually begins for all of us. We've got a familiar, flat, 2D curvilinear trapezoid perfectly locked between mathematical curves on a standard coordinate plane. That shaded region right there, that is our definite integral. And to find its area, we imagine slicing it up into infinitely thin vertical strips, our representative rectangles, and then just summing them all up.
Okay, let's dive into this, because this right here is where the magic actually happens. Imagine grabbing that flat 2D area and just spinning it continuously around a line like the x-axis. As it whips around, it sweeps through the empty space and generates a completely solid 3D shape, what we call a solid of revolution. Suddenly, that flat shaded region is a real physical object. But how in the world do we find its volume?
Which brings us to section 2, the disk method. It's time to start slicing things up into solid disks.
So, the disk method is absolutely perfect for solid shapes that have no inner holes or cavities. Because our original 2D shape was sitting completely flush against the axis of revolution, spinning it just creates one solid mass. To find the total volume, we mentally slice the object up into infinitely thin, solid, circular disks. Honestly, think of it exactly like stacking up an endless series of different-sized dinner plates.
And this brilliantly illustrates the concept in action. Notice how a sequence of these solid disks actually approximates a smooth, funnel-like volume. The math here is elegant. The area of a circle is just pi times radius squared. In calculus, our radius is simply the height of the curve, our function f of x. By integrating, summing up the infinitesimally thin volumes of all those disks across the entire length of the shape, we get our exact total volume.
Moving right along to section 3, the washer method. Let's talk about what happens when our volumes have cavities.
We use this method when our 3D solid has a tunnel or a cavity running right through the inside of it. Think of the shape of a classic donut, a mechanical washer, or an old-school CD. Because of the hole, we aren't slicing the object into solid plates anymore. Our slices now have holes right in the middle. But the calculation is super intuitive. We find the total outer volume, and we just mathematically subtract the empty inner volume.
See the difference here. On the 2D plane, our area isn't touching the axis of revolution at all. There is a very clear gap. So when we spin that shape around, that gap gets swept into a hollow tunnel running through the center of the solid. To calculate this, we just need to define two things, an outer curve for our outer radius and an inner curve for the inner radius. It's really just a brilliant logical extension of the disk method.
Now for section 4, cylindrical shells. It's time to build with nested hollow tubes.
So, the cylindrical shell method comes to the rescue when using flat slices like disks and washers turns into an absolute mathematical nightmare. Instead of slicing the solid completely perpendicular to the axis like a loaf of bread, we break the solid down into a series of nested, hollow cylindrical tubes. Visualize it like an endless set of cardboard toilet paper rolls or maybe Russian nesting dolls, with each tube fitting perfectly snugly inside the next one.
So the crucial point is how we actually set up our representative rectangle here.
Instead of spinning a flat rectangle around to make a disk, we take a rectangle that is parallel to our axis of rotation, and we literally wrap it all the way around the axis to create one of those hollow cylinders. The volume of that single shell? It's just its circumference times its height times its infinitesimally small thickness. Integrate all those nested shells together, and you've got your total volume.
Section 5. The Golden Rule of Rotation. How to actually choose the right method without losing your mind. Okay, listen closely, because this is the golden rule of rotation, and I cannot emphasize this enough. Knowing this will save you so much frustration. The orientation of your representative 2D rectangle compared to the axis of rotation is absolutely everything. If your rectangle is drawn perpendicular to the axis, you're using the disk or washer method, period. But if your rectangle is drawn parallel to the axis, you must use the shell method. Now, what's really interesting about this slide is that it is essentially your ultimate cheat sheet. It clearly shows how the underlying math dictates the best method to use. For instance, say you're revolving around the y-axis, but your given equation is in terms of x, and it's practically impossible to invert. Well, the shell method is your best friend there. It lets you keep your rectangles parallel to the y-axis so you can just easily integrate with respect to x. The geometry literally dictates the easiest path.
Finally, Section 6, Real-World Calculus. Let's see all of this math actually pay off in the physical world.
Check out this shape. It's mathematically known as a prolate spheroid, which is essentially an ellipsoid. Notice how it's shaped exactly like a rugby ball or an American football? Now, sports manufacturers actually need to know the exact internal volume of this shape to figure out air pressure capacities. How do they do it? They simply take the upper half of a standard 2D ellipse and revolve it completely around the x-axis. Applying the disk method to that simple algebraic curve magically pops out the precise 3D volume of a complex sports ball. Incredible, right?
And let's bring back our hook from the very beginning of the explainer, the dog dish. To find the exact material volume of a heavy, slanted plastic dog bowl, calculus steps right in. First, we define its 2D cross-section as a simple triangle. Now, because the bowl is slanted, the inner and outer radii aren't constant. They change. The inner radius increases linearly from bottom to top, while the outer radius decreases. We map those two varying radii, plug them straight into our washer method formula, integrate the difference of squares, and boom, we know exactly how much material is needed on the factory line.
Before we wrap up, there's another beautifully surprising math fact from our sources I have to share. Did you know the volume of the corner of a room is exactly 1/6 of the corresponding edge length cubed? Elegant, right? But the Pappas-Goldinus theorems take this elegance way further. They elegantly connect the surface area and volume of a solid directly to the distance traveled by its centroid, or center of gravity, during rotation. The volume is literally the 2D area multiplied by the path distance of that center of gravity. It is an absolutely stunning shortcut that perfectly unites geometry and motion.
So, I want to leave you with this. Take a second and just look around whatever room you are in right now. Look at your coffee mug, a lampstand, maybe a water bottle sitting on your desk. How would you slice them up mathematically? Would you use disks, washers, or shells? Once you start viewing the 3D world through this structured calculus lens, seeing the curves, the rotations, the centers of gravity, you'll see the elegant geometry of calculus literally everywhere. Keep analyzing, keep exploring, and thank you so much for learning with me today.